What's up, everybody? Welcome to Kenny Kinetics, where learning is made easy. Today, we are going to be taking a deeper look at what sensory information is processed through the spinocerebellar pathway. So let's go, y'all. Let's dive into this spinal tract. You ever go to the doctor to get a physical done so you can play in whatever sport you're trying out for? You're sitting there during the examination, and then you see your doctor pulls out a Reflex Hammer. I know everybody in their head be thinking, when they hit me with the Reflex Hammer, I'm not gonna kick. I know you had this thought as a kid growing up. So the doctor winds up the Reflex Hammer, getting their precision right to target the patellar tendon. And in your head, you're thinking, you're not gonna kick. But as the Reflex Hammer bangs against your patellar tendon, you end up kicking. In your head, you're like, man, they got me again. So why do you end up kicking even though you are telling your body not to kick? Well, in order to understand this, we need to take a deeper look at the quadriceps, the hamstrings, and the muscle spindles inside of them. So here is a quadriceps muscle. This muscle here is also known as the extrafusal fiber. And here in the middle of the muscle belly of the quadriceps is the muscle spindle. Every muscle within the body has muscle spindles located within the muscle belly of that muscle. The muscle spindle has two fibers within it. One is known as the nuclear chain fiber, and the other is known as the nuclear bag fiber. The nuclear chain fiber is responsible for detecting the length of change within the muscle, and the nuclear bag fiber is responsible for detecting the length of change within the muscle, as well as the rate of change within the muscle. Together, the nuclear bag and nuclear chain fibers make up the muscle spindle, and these are collectively known as the intrafusal fiber. Side note from the knee-jerk reflex we are looking at, I want to quickly go over the golgi tendon organ. They are located within tendons of all muscles, and they pick up on the force or load applied to the muscle. Say you are at the gym and you want to try to curl a 100-pound dumbbell, even though you've only been able to curl 30 pounds. When you pick up the 100-pound dumbbell and you're trying to curl it, the golgi tendon organ senses an increased load on the biceps muscle and goes, whoa, big fella, you got too much dip on your chip. AKA, what are you doing? You know you can't curl that. So in order to avoid any damage to the biceps, the golgi tendon organ forces the biceps to relax. Alright, I had to cover the golgi tendon organ real quick because it is also involved in sending unconscious information through the spinocerebellar tract. But now we're going to go back to the muscle spindle. So as the muscle fiber begins to lengthen and shorten, the muscle spindles detect the length of change as well as how fast it is changing, and it sends this impulse to the spinal cord and the spinocerebellar tract. Let's take a closer look on how your legs kick on its own even though you're telling it not to. So the players involved are the quadriceps, the hamstrings, and the muscle spindles located within the quadriceps. The quadriceps are connected to the patellar tendon as it attaches to the tibial tuberosity. So when the doctor strikes the patellar tendon, this gets transferred to the quadriceps muscle and it causes it to stretch a little. The muscle spindle picks up on the length of change and rate of change in the quadriceps and sends this information to the spinal cord through its afferent neuron. Here it synapses with a motor neuron that controls the quadriceps and activates it to kick the leg. The muscle spindle also synapses with an interneuron, which synapses with the motor neuron for the hamstrings. Here, the motor neuron tells the hamstrings to relax, so the quadriceps are able to extend the knee without inhibition from the hamstrings. This is why you kick when the doctor taps your patellar tendon, even though you are fighting not to. So anytime a muscle lengthens or shortens, the muscle spindles within these muscles sense the length and rate of change in the muscle and sends it to the spinocerebellar tract. In order to process unconscious information, the spinocerebellar tract has to receive information from muscle spindles and golgi tendon organs within the body. Again, the muscle spindle detects the length of change in muscles and the rate of change in muscles, and the golgi tendon organs detect the force or load applied to muscle. The spinocerebellar tract has three main tracts that we are going to cover today: the dorsal spinocerebellar tract, cuneocerebellar tract, and ventral spinocerebellar tract. The ventral spinocerebellar tract receives unconscious proprioception from L2 and down. The dorsal spinocerebellar tract receives unconscious proprioception from T1 to L2. And the cuneocerebellar tract receives unconscious proprioception from C8 and up. Here in the spinal cord, you can see where the dorsal spinocerebellar tract and the ventral spinocerebellar tracts are located. First, we will be looking at the dorsal spinocerebellar tract. Length and rate of change in muscles and the force and load applied to tendons and muscles from T1 to L2 are sent to the posterior aspect of the spinal cord through the dorsal root ganglion. Remember the rex lamina from the spinothalamic video? There are 10 total. The one to remember for this pathway is rex lamina 7, which is called the nucleus dorsalis or Clark's nucleus. It is responsible for receiving and transmitting unconscious proprioception. Here, it synapses with the second order neuron, then travels through the dorsal spinocerebellar tract until it ascends and reaches the medulla. In the medulla is the inferior cerebellar peduncle. Here, the signal travels through the inferior cerebellar peduncle and relays the information from all the muscle spindles and golgi tendon organs and muscles and tendons between T1 and L2 to the cerebellum. All conscious proprioception is processed through the cerebrum, but since the information is going to the cerebellum, it is getting processed unconsciously. We will discuss in future videos in detail how the cerebellum processes this information to control motor output. Let's recap the order in which unconscious proprioception travels through the dorsal spinocerebellar tract. Number 1. Information from muscle spindles and golgi tendon organs in all muscles and tendons between T1 and L2 enter the posterior aspect of the spinal cord through the dorsal root ganglion. This is known as the first order neuron. Number 2. The first order neuron synapses with the second order neuron in the nucleus dorsalis or Clark's nucleus. Number 3. The signal stays ipsilateral and enters the dorsal spinocerebellar tract. Number 4. The signal then ascends up into the medulla and enters the cerebellum through the inferior cerebellar peduncle. Here, it relays the unconscious proprioceptive information to the cerebellum. Now let's take a look at the cuneocerebellar tract. Length and rate of change in muscles and the force and load applied to tendons and muscles from C8 and up and to the posterior aspect of the spinal cord through the dorsal root ganglion. The signal ascends up into the medulla. Within the medulla is the lateral or accessory cuneate nucleus. The signal travels to the lateral or accessory cuneate nucleus and synapses with the second order neuron. It then travels through the inferior cerebellar peduncle and enters the cerebellum. Here's a quick recap of the cuneocerebellar tract. Number 1. Sensory information from C8 and up enter the dorsal root ganglion of the spinal cord. This is known as the first order neuron. Number 2. Signal travels into the medulla and then synapses with the second order neuron in the lateral or accessory cuneate nucleus. Number 3. Signal enters the cerebellum through the inferior peduncle and relays its sensory information. Last but not least is the ventral spinocerebellar tract. Length and rate of change in muscles and force and load applied to tendons and muscles from L2 and down enter the posterior aspect of the spinal cord through the dorsal root ganglion. Here, the signal synapses with the second order neuron. The signal then decussates or crosses over the middle of the spinal cord and enters the ventral spinocerebellar tract. Here it enters the ventral spinocerebellar tract and ascends up the brainstem until it reaches the midbrain. Within the midbrain is the superior cerebellar peduncle. The signal travels through the superior cerebellar peduncle and enters the cerebellum. Within the cerebellum, the signal travels back to the ipsilateral side and then it relays its sensory information. Now let's recap the order in which the signal travels through the ventral spinocerebellar tract. Number 1. Sensory information from L2 and below enter the spinal cord through the dorsal root ganglion. Number 2. The signal synapses with the second order neuron in the spinal cord. Number 3. The signal decussates or crosses over the middle of the spinal cord and travels through the ventral spinocerebellar tract. Number 4. The signal travels through the medulla, pons, and midbrain and enters the cerebellum through the superior cerebellar peduncle. Number 5. The signal crosses back over to the ipsilateral side in which the sensory information originally came from. Alright everyone, thank you so much for watching. Make sure you subscribe, like, share, and leave comments. This completes all of the ascending spinal tract videos. Tune into my next video, where I outline the corticospinal tract. Thanks for watching.